Hey there, today's discussion is on algebraic limits and continuity. Finding limits, as we found in the last lesson, numerically and graphically, can be time-consuming. So we need to develop a method that is quicker to evaluate limits for a variety of different functions. And once we accomplish that, we can study the importance of continuity. So here are a list of properties of limits. We have the sum rule, the difference rule, a constant multiple rule, product, quotient, power, and root rule. So we'll go over some of them together here. So our first example, let's use the limit properties to find the limit as x approaches 4 of x squared minus 3x plus 7. So we know that the limit as x approaches 4 of the value of x is 4 because it states x is approaching 4. So it must be 4. So therefore we can use the power rule, number 4 there. Excuse me, not number 4, the power rule number 6 there. So as the limit as x approaches 4 of x squared, that means we want to find the limit of x squared. And we know that this whole piece here is equivalent to 4, so then 4 squared is 16. Moving on to the second one, we can use the constant multiple rule. So I want to know as the limit approaches, as x approaches 4 of negative 3x, I know that's the same as taking negative 3 times the limit of x, and I know that the limit of x is 4, so negative 3 times 4 is negative 12. The limit of a constant is the constant, so we can just leave 7 as positive 7. And finally, we can use the sum or difference rule to actually find the limit of all of them together. So 16 minus 12 plus 7 is 11. Well, then you're probably asking, well, why don't I just plug it in? That leads us to the theorem. The limits of a rational function for any rational function f with the domain of f, the limit as x approaches a of the function is f of a itself. This tells us that we can substitute x equal to a directly into the rational function to find the limit only if it does actually truly exist. So let's find the limit as x approaches 2 of the rational function x squared minus 5x cubed plus x squared minus 7. So we can use the above theorem, we can find the limit through substitution. So as x approaches 2, let's substitute in 2 for everywhere where we see x. So 2 to the 4th minus 5 times 2 cubed plus 2 squared minus 7. When we multiply and we use our powers, we get 16 minus 40 plus 4 minus 7. Adding and subtracting gives us negative 27. So the limit as x approaches 2 is negative 27. Let's find the limit as x approaches 0 of the square root of x squared minus 3x plus 2. This follows the above theorem in combination with the root rule, so we can find the limit by substitution. So I'm going to substitute 0 in everywhere where we see x. 0 squared minus 3 times 0 plus 2 gives us the square root of 2. Let's find the limit as x approaches negative 3 of the rational function x squared minus x minus 12 over x plus 3. We're running into a problem here because we cannot substitute negative 3 in for x, as it would result in a 0 in our denominator. So f of x does not exist. So we cannot use the rational function rule. And the quotient rule is also not met. The quotient rule from the first couple of slides states that the bottom number cannot equal 0. And since it does, we have a problem. So we're going to have to go back to getting as close as we can to negative 3 to find the limit numerically and or graphically like we did in the previous lesson. So we need to approach x at -3 from the left side and the right side in hopes that we do come up with the same number. Notice when I graphed it here, there is a hole at -3 because it doesn't exist there. So when I plug in -3.1, -3.01, and -3.001, I see we are approaching -7. Let's approach -3 from the right-hand side. So -2.9, -2.99, and -2.999. Here I see I'm also approaching -7. Therefore, the limit as x approaches -3 of our rational function is -7. But perhaps there's a way we can do this algebraically. So if I start with our rational function, I notice that I can factor my numerator by finding two numbers that multiply to -12 and add to -1, which are +3 and -4. Since there's nothing in front of x squared, we can jump to our factored form of x plus 3x minus 4. Since everything's in multiplication, I can cancel off the x plus 3's, leaving me with x minus 4. Now we have a limit of rational functions, so I can actually find the limit as x approaches -3 using this reduced function value that we found. So when I substitute -3 in for x, we get -3 minus 4, which is -7, which is what we found using our table of values and graphically. Just want to remind you that 0 divided by 0 is not 0. And when we divide by 0, our answer is undefined, so be careful with that. Let's find the limit as h approaches 0 of the function 3x squared plus 3xh plus h squared. Notice here that I have the variable x and h. We're going to treat x as a constant since we're only interested in what happens as h approaches 0. And since it is a rational function, we can substitute 0 in wherever we see h and simplify, giving us 3x squared plus 3x times 0 plus 0 squared. Simplifying gives us simply 3x squared. Now that we know a little bit about an alternative way in which we can find the limit using substitution, we want to define a continuous function. So a continuous function at x equals a particular number happens if all three of these exist. We can find f of a, the limit as x approaches a exists, and the limit as x approaches a is equivalent to f of a. All three of these must happen in order for a function to be continuous. A function is continuous over an interval if it is continuous at each point in that interval. If it is not continuous at x equals a, we say that f is discontinuous or has discontinuity at x equals a. So if any part of the continuity definition fails, then the function is discontinuous. So all three, a, b, and c, must work. If even one of them does not, then it is not continuous or it's discontinuous. So let's take a look at these two graphs here. On the left, I have y equals 1 over x minus 3. We can say that this is not continuous over the interval from -infinity to +infinity because we see that 3 is not in the domain. Thus, we cannot keep tracing our equation or our lines here at 3 because we're going to fall down, we're going to get close, but then how am I supposed to get back over here? We can say that the function, though, is continuous over two different intervals. It's continuous from -infinity all the way to 3. We can skip 3 and begin at 3 and go to infinity, and it continues its continuity. Looking at the graph on the right, notice I have x when x is less than 1. There is a hole here, and at 1, this is included. So excluded here, included down here. Notice that this is also not continuous from negative infinity to positive infinity, because as I trace my graph, I stop. I have to hop down here to continue. So it's not a nice continuous line. So we approach 4 coming from the left. However, we approach 0 coming from the right. So we're approaching two different locations. However, just like the previous example, we can say that the function is continuous over the two intervals. From negative infinity to 1, skip and start back at 1 and continue to infinity. So notice that we cannot have any holes or jumps in the graph to be continuous. We should be able to use our pencil and trace over the entire graph without skipping or jumping or having gaps or whatnot in them. Let's determine whether the function given by 2x plus 3 is continuous at x equals 4. So first we need to know that f of 4 exists. So I can plug in 4, and when I do, I get 8 plus 3, which is 11. So part A exists, f of 4. Further, we can verify algebraically and graphically that the limit as x approaches 4 certainly does exist. Because it is a rational function, we can plug in 4 and see that it works. And since as for the limit as x approaches 4 is equal also to 11, and f of 4 equals to 11, we have satisfied all three parts. So we can say that f of x equals 2x plus 3 is continuous over the entire real number line. Further, we know that 2x plus 3 is a linear line, and it would be continuous visually, but now we've proved it algebraically. Is the function given by f of x equal to x squared minus 5 continuous at x equals 3? Why or why not? Using our theorem on rational functions, we know that we can plug in 3 for f of x so that we get 3 squared minus 5, which is 9 minus 5, which equals 4. Now we can plug in f of 3, giving us 3 squared minus 5, which is 9 minus 5, which equals 4. Okay. And since the limit of x as x approaches 3 is equal to f of 3, we can say that all three parts of the definition are satisfied and that f of x is continuous at x equals 3. Visually, we can see this as well. Let's look at this following function. We want to know if it's continuous at x equals negative 2. Notice that on the left-hand side, we do not include negative 2 here because of the piecewise function, and down below that this piece is included because of this part down here. So for the function to be continuous, we must have the limit of x as it approaches negative 2 equal to g of negative 2. We can easily find g of negative 2. Since negative 2 is greater than or equal to negative 2, we will plug in negative 2 minus 1, which gives us negative 3. And now we need to find the limit as x approaches negative 2. To do that, we need to look at the left hand and the right hand limits to verify that it exists. So let's start with negative 2 approaching from the left side. When I approach negative 2 from the left side, I'm using the half x plus 3 equation because I'm looking for values that are less than negative 2. So when I plug in negative 2 to that top one, I end up with half times negative 2 plus 3, which is equal to negative 1 plus 3, or 2. Now let's look at the limit as we approach negative 2 from the right-hand side. Now, because we are looking for values that are slightly greater than or equal to negative 2, we're going to use this bottom equation. So when I plug in negative 2 minus 1, we get negative 3. This is a problem. So since the limit as x approaches negative 2 from the left does not equal the limit as x approaches negative 2 from the right, we can verify from our last lesson that the limit does not exist here because they would have to be equivalent to each other for that limit to exist. And since the limit does not exist, we do not satisfy